Tonight, we follow the quiet traces of Mars's lost water, a story preserved in ancient valleys, buried ice, and the thin silence of its atmosphere. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. Mars carries a quiet record of its past across its surface, almost like a memory preserved in stone. When scientists began to study high-resolution images from orbit, they noticed shapes that could not have come from wind or volcanic activity alone. Long, winding valleys stretch for hundreds of kilometers, their curves as smooth as river paths on Earth. Some of these channels join together the same way. Tributaries merge into a main river, suggesting a network that once carried flowing water. At the edges of ancient basins, there are raised, uneven lines that resemble shorelines, natural boundaries made when water repeatedly touched and retreated from the same rock. Minerals on Mars add another layer of evidence. Clays, for example, form only when water interacts with rock for long periods at moderate temperatures. Their presence tells us that Mars once had stable bodies of water, not just brief or violent floods. Sulfate minerals, found in layered deposits, reveal that some lakes slowly evaporated over time. These minerals act like chemical time capsules. They preserve the conditions under which they form, making them crucial clues in reconstructing the planet's watery past. Another important piece of evidence lies in Mars's atmosphere. Scientists measure the ratio between two forms of hydrogen, the regular kind and a heavier version known as deuterium. On Earth, the two exist in predictable proportions. On Mars, however, deuterium is far more abundant. This imbalance occurs because lighter hydrogen atoms escape into space more easily than heavier ones. If Mars once had large amounts of water, sunlight would break some of it into hydrogen and oxygen. Over billions of years, the lighter hydrogen would slowly drift away into space, leaving behind a higher concentration of deuterium. The extreme enrichment we observe today tells us that Mars has lost the equivalent of an entire global ocean. Ancient lake beds offer even more detail. The Curiosity rover discovered finely layered sediments inside Gale crater patterns that form when calm water deposits dust and minerals over long periods. These layers stack like pages in a book, each one recording a stable environment where water once pooled. Curiosity also detected organic molecules, which do not prove life, but do show that Mars had the chemical building blocks needed for complex chemistry. Taken together, all of these clues create a clear and consistent picture. Mars was once warmer and wetter, wrapped in a thicker atmosphere incapable of supporting lakes, rivers, and perhaps even a northern ocean. Today, the planet is cold and dry, its air thin, and its surface exposed to space. Yet the traces of its blue past remain everywhere, in the shapes of its valleys, in the chemistry of its minerals, and in the silent, depleted atmosphere that holds the memory of an ocean long gone. Mars did not lose its water all at once. It happened slowly, through a long and silent unraveling of the atmosphere. To understand this, imagine the planet billions of years ago, wrapped in a thicker layer of air that could trap heat and keep water in liquid form. Lakes and rivers could exist only because this atmosphere acted like a blanket, holding warmth against the planet's surface. But Mars is a small world, only about half the size of Earth. Smaller planets cool more quickly, and as the interior of Mars cooled, the magnetic field that once protected its atmosphere began to fade. A magnetic field acts like a shield, guiding harmful solar particles around the planet instead of letting them strike the atmosphere directly. When this shield weakened, the atmosphere became exposed. The sun constantly releases a stream of charged particles known as the solar wind. On Earth, our magnetic field deflects most of it. But on Mars, the solar wind was free to hit the air molecules at full strength. Over millions of years, these particles knocked atmospheric gases into space. It was not a violent explosion, but a steady erosion, like wind slowly shaping a rock. Molecules of carbon dioxide, nitrogen, and hydrogen drifted away into the void, thinning the air piece by piece. As the atmosphere lost its density, Mars could no longer keep the warmth it once held. Temperatures dropped, and the air pressure fell so low that liquid water could no longer exist on the surface. Even if the sun provided enough heat during the day, the water would either freeze instantly or evaporate directly into the thin air. The loss of atmosphere created a feedback loop. Less air meant colder temperatures, and colder temperatures meant more water turning to ice or vapor and escaping. Scientists study this process through data collected by orbiters like NASA's MAVEN mission. MAVEN observes how solar wind strips particles from the Martian atmosphere even today. It measures the rate of loss, the energy of incoming solar particles, and the composition of gases escaping into space. These modern measurements help researchers reconstruct what happened billions of years ago, showing how quickly the early atmosphere may have disappeared. Scientists also use isotopes, different versions of the same element, to trace atmospheric loss. For example, they compare lighter and heavier forms of oxygen and carbon. Lighter isotopes escape into space more easily, leaving behind an atmosphere enriched in heavier isotopes. This change offers a quiet but powerful record of how much gas has vanished over time. Another key factor is Mars's weak gravity. Because the planet is smaller, its gravity is not strong enough to hold onto light gases like hydrogen. When water molecules break apart due to sunlight, the hydrogen quickly rises to the top of the atmosphere and escapes, accelerating the drying of the planet. Together, these mechanisms, loss of magnetic protection, erosion by the solar wind, chemical breakdown of water, and weak gravity, created the slow collapse of the Martian atmosphere. This collapse changed everything. Mars shifted from a stable world with lakes and rivers to the dry and frozen desert we see today. The disappearance of the atmosphere is not just an isolated event, but a planetary transformation. It reshaped the surface, removed the warmth, erased oceans, and left behind the thin whisper of air that now surrounds the planet. In that thin air lies a story of change, written not in sudden events, but in the slow, steady breath of a world losing its shield over billions of years. Hydrogen is the lightest element in the universe, and on Mars, it became the first part of water to disappear. To understand how this happened, imagine the upper layers of Mars's atmosphere billions of years ago. At that time, sunlight struck water vapor and broke it apart into hydrogen and oxygen. This process, called photodissociation, happens naturally whenever ultraviolet light interacts with molecules. The two elements then drift upward, pushed slowly towards space. Hydrogen, being extremely light, rises higher than oxygen. In the thin upper atmosphere of early Mars, hydrogen was only loosely held by gravity. Once the hydrogen reached the outermost layer, it encountered a constant and powerful force, the solar wind. The solar wind is a steady stream of charged particles, mostly protons and electrons, flowing outward from the sun at high speeds. On Earth, the magnetic field deflects most of these particles, creating the familiar auroras near the poles. But on Mars, after its magnetic field faded, the solar wind had direct access to the atmosphere. The particles slammed into hydrogen atoms and pushed them away into space. Even a small force, applied over millions of years, can carry away enormous amounts of gas. This escape of hydrogen played a critical role in drying out Mars. Water is made of 2 hydrogen atoms and 1 oxygen atom. Once the hydrogen drifted into space, the oxygen left behind could not easily recombine into water. Some of it reacted with rocks, forming oxides that gave Mars its red color. The rest lingered in the atmosphere until it, too, was stripped away or bound into minerals. The process was gradual but relentless. Data from NASA's MAVEN mission shows that solar wind stripping still occurs today. MAVEN measures how many particles escape each second and how the rate increases during solar storms when the sun becomes more active. Even now, billions of tons of gases have been eroded from Mars's atmosphere by this invisible river of solar particles. The loss of hydrogen is also recorded in the planet's isotopes. Hydrogen has a heavier version called deuterium. Lighter hydrogen escapes more easily, while deuterium remains behind. Over time, this leaves behind a higher ratio of deuterium in the remaining water and atmosphere. The extreme enrichment of deuterium on Mars tells scientists that huge amounts of hydrogen have been lost, far more than what could be explained by the current amount of ice or vapor. Another important factor is the structure of the atmosphere itself. As Mars cooled and its air thinned, the upper atmosphere expanded under sunlight, giving hydrogen more room to rise. The thinner the air became, the easier it was for the solar wind to scoop the hydrogen away. This created a feedback cycle. Less atmosphere allowed more hydrogen escape, which in turn reduced the water available to replenish the air. Hydrogen loss also influenced the planet's climate. Without hydrogen, water molecules could not form in large quantities. Less water meant less capacity for heat retention and less potential for cloud formation. The drying atmosphere made surface temperatures even colder, reinforcing the shift toward a frozen world. Taken together, these processes reveal a planet slowly losing its most essential ingredient for life. Hydrogen drifted upward, sunlight split water apart, and the solar wind carried the fragments away. The escape was not loud or dramatic. It was quiet, steady, and unstoppable. Over billions of years, this small but continuous removal of hydrogen erased Mars's oceans and transformed it from a watery world into the desert-like planet we see today. The story of hydrogen loss on Mars is ultimately a story about vulnerability. Without a magnetic shield, without strong gravity, and without enough warmth, the planet could not hold on to the building blocks of water. The solar wind did what running rivers and deep oceans could not resist. It stripped Mars of the element that once made it blue. When Mars began losing its atmosphere, the water on its surface could no longer remain stable. Liquid water needs both warmth and pressure to exist. And as Mars grew colder and its air thinned, water began to disappear into space through several connected processes. The first step was evaporation. With low air pressure, water no longer behaved the way it does on Earth. Instead of remaining as liquid, it shifted directly from ice to vapor. This vapor then rose into the upper atmosphere, where sunlight broke the molecules apart into hydrogen and oxygen. Hydrogen escaped easily because it is extremely light. Even the weak pull of sunlight could push hydrogen atoms upward until they drifted away into space. Oxygen, being heavier, did not escape as quickly. Some oxygen reacted with surface rocks, forming iron oxides that gave Mars its familiar red color. The rest was gradually lost to space through interactions with the solar wind. During periods of intense solar activity, the rate of escape increased. Solar storms, which release bursts of energetic particles, hit the atmosphere and accelerated the loss of both hydrogen and oxygen. NASA's MAVEN mission has observed this effect in real time, showing how the escape rate can rise dramatically during these events. Another contributor to water loss was the planet's cooling interior. As Mars cooled, volcanic activity decreased. Volcanoes on early Mars once released water vapor and gases into the atmosphere, helping maintain pressure. When volcanic activity faded, the atmosphere stopped being replenished. With no new gases rising from within the planet, the atmosphere continued its slow decline, allowing even more water vapor to escape. Over millions of years, these processes created a persistent leak. Water rose from the surface, broke apart in sunlight, and disappeared into space, one atom at a time. What remained froze at the poles or became trapped in rocks, but the rest drifted away into the void. The escape of water into space is not a single event, but a sequence of gentle, interconnected steps. Each one by itself seems small, yet together they transformed the planet. The loss of water marks the shift from a world that could support rivers and lakes to one that now holds only thin frost and buried ice beneath its silent surface. Not all of Mars's water escaped into space. A large portion remains on the planet, preserved quietly as ice or locked inside minerals. When scientists study the Martian poles, they see vast caps of frozen water mixed with layers of carbon dioxide ice. These polar deposits are thick and stable, and radar data suggests that if all the ice melted, it could create a shallow global ocean several meters deep. Even in its frozen state, the amount of water stored at the poles is significant. Beyond the poles, water also lies hidden beneath the surface. Orbiters equipped with radar have detected buried ice in mid-latitude regions, protected under layers of dust and rock. These underground deposits likely formed when Mars was warmer and had a thicker atmosphere. As the climate changed, the water froze and became trapped below ground, where it remains insulated from sunlight and atmospheric growth. Another major reservoir lies within the rocks themselves. Many Martian minerals contain water locked at the molecular level. These hydrated minerals, such as clays and sulfates, form only when liquid water interacts with rock for long periods. Their presence shows that Mars once hosted lakes, streams, and possibly long-lasting groundwater systems. Because the water is part of the mineral structure, it cannot evaporate or escape easily. The atmosphere also holds a thin trace of water vapor. Though the air on Mars is extremely dry, a small amount of water cycles seasonally between ice, vapor, and frost. During warmer months, ice at the poles and ground ice in certain areas sublimates into the air, forming faint clouds and thin layers of overnight frost. It is a fragile cycle, but it shows that Mars still supports a slow movement of water. Robotic missions have confirmed these hidden reservoirs. The Phoenix lander uncovered pure ice just beneath the surface in the northern plains. The Perseverance rover has found minerals that formed in long-standing water, strengthening the evidence for ancient lakes. These discoveries reveal that Mars's water never truly disappeared. It changed form. The water that remains on Mars is essential to understanding the planet's history and future. Subsurface ice could support future human missions by providing drinking water, oxygen, and even fuel. Hydrated minerals
preserve clues about the environments that once existed, helping scientists piece together the story of early Mars. Although the oceans are gone, the planet still holds the memory of its watery past.
Frozen in ice and captured in rock, Mars's remaining water stands as a quiet reminder that the planet was once far more active, warmer, and capable of hosting long-lasting liquid water on its surface. Mars once had a magnetic field, a protective shield created by the motion of molten metal deep inside its core. This field played a critical role in keeping the planet warm and wet. It prevented the solar wind, a stream of charged particles from the sun, from directly striking the atmosphere. As long as this shield existed, Mars could hold onto its air, maintain surface pressure, and support liquid water. But billions of years ago, something changed inside the planet. Mars is much smaller than Earth, and small planets cool more quickly. As the interior temperature dropped, the molten core slowed its movement. Without enough heat and motion, the magnetic field grew weaker and eventually collapsed. This collapse happened gradually, but its consequences were enormous. Once the magnetic shield disappeared, the atmosphere became exposed. Solar wind particles began to strike the upper layers of air, knocking gas molecules into space. Over time, this stripping process removed large amounts of carbon dioxide and nitrogen, thinning the atmosphere until it could no longer trap enough heat to support liquid water. Evidence of this ancient magnetic field is preserved in the planet's crust. Certain rocks on Mars are magnetized, meaning they formed at a time when the planet still had a global magnetic field. These rocks act like geological fossils, holding a magnetic signature of a lost era. By mapping these magnetic patterns from orbit, scientists discovered that Mars's early field was strong but disappeared more than 4 billion years ago. NASA's MAVEN mission helps researchers understand what happened after the field collapsed. MAVEN observes how the solar wind continues to strip away atmospheric particles today, showing how much more dramatic the loss would have been when the magnetic field vanished. The failure of the magnetic field marks one of the most important turning points in Martian history. It transformed the planet from a world capable of supporting rivers, lakes, and possibly a northern ocean into the cold, thin-air desert we see now. Without its magnetic shield, Mars became vulnerable, and the slow erosion of its atmosphere changed its climate forever. In the early history of Mars, the planet was far more geologically active than it is today. Its interior held more heat, its crust was thinner, and volcanic activity shaped much of its surface. These volcanoes were not small or brief events. Some were enormous, forming the largest volcanoes known in the solar system, most famously Olympus Mons, a shield volcano nearly 3 times the height of Mount Everest. Volcanoes played an essential role in Mars's early climate. When magma rose from deep within the planet, it carried gases trapped in the interior. These gases, water vapor, carbon dioxide, sulfur compounds, were released into the atmosphere during eruptions. On young Mars, this steady outgassing built a thicker, warmer atmosphere that could trap heat and support liquid water on the surface. In this way, volcanic activity acted as a natural pump, supplying new air and new water to the environment. But Mars is a small world. smaller planets lose heat faster than larger ones. Over time, Mars's interior cooled, and the engines that powered its volcanic activity began to slow. The planet's crust thickened, making it more difficult for magma to rise to the surface. Eruptions became less frequent, less intense, and eventually rare. As the volcanic activity declined, the atmosphere stopped receiving fresh gases. This decline mattered deeply. Carbon dioxide, released during eruptions, is a powerful greenhouse gas. It traps heat and helps maintain stable temperatures. When volcanic outgassing faded, the atmosphere gradually lost one of its key sources of replenishment. Combined with the loss of the magnetic field, the thinning atmosphere could no longer hold enough heat to keep water stable. The surface grew colder, and any remaining liquid water froze or evaporated into the thin air. Cooling inside the planet also changed the way water behaved underground. In the early warm period, groundwater flowed through cracks and layers in the crust, transporting minerals and forming lakes below the surface. As the planet cooled, this groundwater began to freeze. Some of it became locked in place as subsurface ice, forming the hidden glaciers that radar instruments detect today. Evidence of this transition remains etched into the Martian landscape. Lava plains, collapsed volcanic vents, and wide calderas reveal a once active interior. The presence of volcanic minerals in ancient lake beds shows that eruptions and water interacted frequently. Certain rocks contain both volcanic components and water-altered minerals, offering a quiet record of a world where fire and water coexisted. The end of major volcanic activity marked a shift in Mars's long-term climate. Without continued heat from the interior, the crust became more stable and rigid. Without volcanic gases, the atmosphere grew thin. And without warmth, the water that once shaped valleys and plains either froze beneath the surface or vanished into space. Today, Mars's volcanoes stand silent, their enormous shapes frozen in time. They remind us that the planet once had the internal power to reshape its own environment. The cooling of the interior was not a sudden collapse, but a slow fading of geological energy, an aging process that changed the entire character of the planet. Through volcanoes, heat loss, and interior cooling, Mars moved from a warm and dynamic world to the cold, quiet desert we see now. These changes, taking place over hundreds of millions of years, played a critical role in the disappearance of water from the surface and the transformation of the planet's climate. Mars may seem dry and silent, but its polar regions hold one of the most dynamic systems on the entire planet. The North and South poles are capped with layers of frozen water ice and carbon dioxide ice. These caps expand and shrink with the changing seasons, creating a subtle but persistent water cycle that still operates today, even in Mars's thin and cold atmosphere. The northern ice cap is mostly water ice. In winter, temperatures drop so low that carbon dioxide from the atmosphere freezes directly onto the surface, adding a seasonal layer of dry ice. When spring sunlight returns, this dry ice sublimates, turning from solid directly into gas, and reveals the thicker, more permanent water ice layers beneath. Radar instruments have shown that these deep layers form a stack of frozen history, each one capturing a different period of climate on Mars. The southern pole works differently. Its cap contains a much larger portion of carbon dioxide ice, some of which remains permanently frozen. Scientists believe that this permanent dry ice layer holds enough carbon dioxide to significantly thicken the atmosphere if it ever warmed enough to release it. But for now, the air is too cold and thin, so the ice remains locked in place. These seasonal cycles move small amounts of water vapor around the planet. As sunlight warms the poles, tiny quantities of water sublimate into the atmosphere. Mars's thin air cannot hold much moisture, but even this faint vapor matters. Winds carry it toward colder regions, where it can condense again as frost. Some nights, a thin layer of frost forms on rocks and soil, sparkling in the morning light before it fades back into vapor. Occasionally, the vapor forms clouds. These are not thick or dramatic like clouds on Earth. Instead, they drift softly across the sky, delicate white strands of frozen crystals. Rovers have captured images of these clouds, glowing faintly as they pass overhead, offering visual proof that Mars still maintains a gentle, quiet cycle of water. The polar caps themselves also reveal clues about ancient climates. Their layered structure resembles tree rings or sediment beds. Some layers are rich in dust, formed during windy and dusty periods. Others contain cleaner ice, deposited during calmer, colder eras. By studying these layers with radar, scientists can reconstruct past patterns of temperature, storms, and even changes in the tilt of Mars's orbit. These seasonal cycles also affect the distribution of subsurface ice. When the poles release small amounts of vapor, the moisture can travel south and settle underground, forming ice just below the surface. Over thousands of years, these slow movements have helped shape the hidden glaciers we detect today. Although the modern Martian water cycle is extremely weak compared to Earth's, it still plays a meaningful role. It redistributes frost, shapes the appearance of the poles, and reminds us that Mars is not entirely frozen in time. Instead, it is a world that continues to breathe, though softly, its thin atmosphere and icy poles exchanging water in a quiet rhythm that has lasted for millions of years. The polar ice caps and seasonal cycles show that water never truly left Mars. It simply adapted to the planet's new conditions, settling into forms that could survive the cold and thin air. Through these frozen reservoirs and gentle movements of vapor, Mars continued to hold on to a piece of its ancient, watery past. A significant portion of Mars's ancient water did not flow away, freeze on the surface, or escape into space. Instead, it became part of the planet itself, locked deep within rocks through a process known as chemical hydration. This hidden water is not liquid or ice, but water bound inside the crystal structure of minerals. Although it cannot move freely, it carries a detailed record of the planet's wetter past. Hydrated minerals form when liquid water reacts with certain types of rock. On Mars, this happened billions of years ago, when streams, lakes, and groundwater systems were far more common. Water seeped through volcanic basalts, breaking down their structure and creating clays, sulfates, and other alteration minerals. In these minerals, water molecules become trapped as hydroxyl groups, chemical fragments that stay locked within the rock until it is heated to extremely high temperatures. These clays are particularly important. They form only in environments where water is present for long durations, often at moderate temperatures. The presence of widespread clays suggests that Mars once had stable bodies of water, not just short-lived floods. Rover missions have found clay-rich layers in ancient lake beds, confirming that water interacted with Martian rocks over long periods. These layers preserve a geological memory of an environment that could support more complex chemistry. Sulfates provide another clue. These minerals often form as water evaporates. Their presence indicates that many Martian lakes dried slowly, leaving behind mineral deposits as the water receded. Some regions contain thick sulfate-rich layers, suggesting repeated cycles of flooding and evaporation. These minerals tell scientists that Mars once experienced climate fluctuations capable of sustaining water for extended periods before eventually drying out. Hydrated rocks also hold insights about the chemistry of ancient water. By analyzing the minerals, scientists can determine whether the water was acidic, salty, or neutral. Some areas show evidence of neutral pH conditions, which would have been favorable for life. Other regions indicate more acidic water, shaped by volcanic gases. Each mineral acts like a snapshot, recording the state of the water that helped form it. The existence of hydrated minerals across large portions of the planet shows that chemical trapping was one of the most important processes for retaining water. While the atmosphere thinned and the oceans disappeared, the rocks continued to hold onto a significant part of Mars's original water inventory. These minerals are so stable that, even today, they contain water that has been trapped for billions of years. Current missions provide ongoing insights into these hidden reservoirs. The Perseverance rover analyzes minerals in Jezero Crater, a location chosen specifically because it once hosted a large lake. Orbital spectrometers map hydrated minerals across the planet, revealing just how widespread water-rock interactions once were. These observations confirm that chemical trapping represents a major chapter in the story of Martian water. This chemically bound water also has implications for future exploration. If humans eventually travel to Mars, hydrated minerals could serve as a potential source of water. Heating these rocks to high enough temperatures would release the trapped water, offering a way to extract resources in environments where surface ice is scarce. The chemical trapping of water in rocks is a quiet, concealed process, but its impact is enormous. It preserved ancient environments, protected water through billions of years of climate change, and left behind a geological archive that scientists continue to read today. Through these minerals, Mars still carries the imprint of its watery past, hidden within the very structure of its crust. Mars is famous for its dust storms, events so large and persistent that they can cover the entire planet in a soft, orange haze for weeks at a time. These storms may look gentle from afar, but they play an important role in how the atmosphere continues to thin and how Mars loses what little water it still has. Even though the storms are not violent, they create conditions that help push gases, including water vapor, higher into the atmosphere, where they can escape into space. The Martian dust is extremely fine, almost like powder. When sunlight warms the surface, the air above begins to rise. This rising motion lifts dust particles from the ground and suspends them in the atmosphere. During certain seasons, especially near southern summer, these lifting motions become stronger. The dust absorbs sunlight, heating the air even more. This creates a feedback cycle where warm, dusty air continues to rise, spreading the storm across larger and larger regions. When a dust storm becomes global, it changes the way Mars's atmosphere behaves. The layer of dust acts like a blanket, trapping heat in the lower atmosphere and raising temperatures by tens of degrees. This warming causes the air to expand upward, As the atmosphere stretches, tiny amounts of water vapor normally confined near the surface are carried to much higher altitudes. In these upper layers, sunlight easily breaks apart the water molecules, freeing hydrogen atoms. Once hydrogen reaches these high altitudes, it becomes vulnerable to escape. The upper atmosphere of Mars is so thin that hydrogen atoms can drift away into space, especially when pushed by the solar wind. Dust storms dramatically increase this process by lifting more water vapor upward and creating more opportunities for hydrogen to escape. NASA's MAVEN mission has directly observed this effect. During a global dust storm in 2018, MAVEN recorded a large increase in hydrogen escape from the atmosphere. The amount of hydrogen drifting away into space rose several times higher than normal, showing that dust storms continue to contribute to the long-term loss of water on Mars. Dust storms also affect the temperature balance of the atmosphere. By heating the lower layers and cooling the upper ones, they create strong vertical temperature differences. These differences help drive winds and turbulence that mix gases and carry them to escape-prone altitudes. Even though Mars's atmosphere is thin, these internal motions keep the process of atmospheric loss active. Another important aspect is that dust storms can last for weeks or months. During this time, the continuous lifting of dust and warming of the atmosphere maintain conditions for water vapor to rise and escape. Over billions of years, this repeated cycle contributed significantly to the gradual dehydration of the planet. The storms also reshape the landscape. As dust moves across the surface, it covers ice deposits, uncovers new ones, and changes how sunlight interacts with the ground. Darker surfaces absorb more heat, reinforcing the atmospheric patterns that lead to future storms. In the end, Martian dust storms are not merely surface-level events. They are powerful climate engines that influence how the atmosphere evolves and how Mars continues to lose water. They show that even in a cold, quiet world, small particles of dust can shape planetary history. Through their gentle but persistent motion, they help drive the slow escape of hydrogen, contributing to the long decline of Mars's once rich water supply. Mars offers one of the clearest examples in the solar system of how a planet's climate can shift from warm and wet to cold and dry. Billions of years ago, Mars had rivers, lakes, and perhaps even a northern ocean. Today, it is a frozen desert with a thin atmosphere. This transformation did not happen instantly. It unfolded across immense spans of time, shaped by processes that reveal universal lessons about how planetary climates evolve. One of the most important lessons Mars gives us is that climate depends heavily on atmospheric thickness. In its early years, Mars had a denser atmosphere, rich in carbon dioxide. This blanket of gas trapped heat from the sun, creating temperatures high enough for liquid water to flow on the surface. But as the atmosphere thinned, the planet lost its ability to retain warmth. Without that insulation, even sunlight could not keep water from freezing or evaporating. Mars shows how sensitive a planet can be when the balance between atmospheric pressure and temperature begins to shift. Another lesson comes from the loss of the magnetic field. When Mars's internal dynamo shut down, the solar wind began to strip the atmosphere away. This process demonstrates how vulnerable an unprotected planet can be. On Earth, our magnetic field shields us from these same forces. Mars's decline illustrates what might happen to a planet if that shield weakens or disappears. It highlights the importance of planetary interiors and how internal heat drives long-term climate stability. Mars also teaches us that climate change can be slow and persistent rather than sudden. Its water did not vanish overnight. Instead, it escaped through a combination of gradual processes: atmospheric thinning, solar wind stripping, chemical reactions in rocks, dust storms lifting vapor upward, and water freezing into the ground. The planet shows how small changes, multiplied across long timescales, can completely reshape a world. The geological record on Mars holds signs of multiple climate phases. Some regions show minerals formed in neutral, mild water, an environment that may have supported early microbial life. Other regions show minerals shaped by acidic water produced by volcanic gases. These shifts suggest that Mars experienced cycles of warming and cooling, wetness and dryness, driven by changes in volcanic activity, atmospheric composition, and even the tilt of the planet's axis. By comparing Mars to Earth, scientists gain insight into how climate systems respond to pressure changes, atmospheric chemistry, and the presence or absence of greenhouse gases. Mars once had the ingredients for a stable climate, but lost them gradually. Earth still has these ingredients, but Mars reminds us that they can change. The planet also helps researchers predict the climates of worlds beyond our solar system. Many exoplanets orbit stars more active than our Sun, where strong stellar winds might strip atmospheres quickly. Mars provides a natural example of how those forces reshape planetary environments over billions of years. In the end, Mars stands as a quiet, powerful reminder that climate is not fixed. It evolves with geology, atmosphere, sunlight, and time. The dry valleys and empty basins we see today were once carved by running water, shaped under a sky far thicker than the one that surrounds the planet now. Through Mars, we learn how fragile a climate can be and how profoundly a planet can change when its protective systems fail. Earth and Mars began with more similarities than their modern appearances suggest. Both had volcanic activity, thick atmospheres, and internal heat capable of generating a magnetic field. But over billions of years, the paths of the two planets diverged drastically, shaped largely by the strength or weakness of their magnetic shields. Comparing Earth's active magnetosphere to Mars's lost one reveals why one planet remained habitable while the other transformed into a cold, dry desert. Earth's magnetic field is generated by the movement of molten iron in its outer core. This process, called the dynamo effect, produces a strong, global magnetic shield that surrounds the planet. The field extends far into space, forming a protective bubble known as the magnetosphere. This shield deflects most of the solar wind, the constant flow of charged particles that streams from the sun. Without this protection, the solar wind would gradually erode Earth's atmosphere, stripping gases away and altering the climate. Mars once had a similar magnetic field. Evidence stored in its crust shows that ancient rocks are permanently magnetized, meaning they formed during a time when Mars still had a strong global field. But because Mars is smaller, its interior cooled faster. As the core cooled, the molten iron slowed, and the dynamo effect weakened until it eventually shut down. Without an active magnetic field, Mars lost its protective bubble. The solar wind struck the atmosphere directly, removing gases that were essential for maintaining pressure and warmth. The difference between the two planets becomes clear when we compare their atmospheres today. Earth still has a thick atmosphere with abundant oxygen, nitrogen, and carbon dioxide, a mixture that supports liquid water and life. Mars, lacking magnetic protection for billions of years, now has an atmosphere less than 1% the pressure of Earth's. It cannot retain heat, cannot sustain liquid water on the surface, and cannot protect itself from solar radiation. Earth's magnetic field also helps maintain climate stability. By preventing atmospheric loss, it allows greenhouse gases like carbon dioxide and water vapor to accumulate naturally, warming the planet. Mars, however, lost much of its carbon dioxide to space or chemical processes and could not replenish it once volcanic activity decreased. The two planets show how the presence or absence of a magnetic shield can dictate whether a world remains habitable over geologic timescales. This contrast provides valuable insight into the conditions required for life on other planets. A world with liquid water but no magnetic field may lose its atmosphere quickly, making long-term habitability unlikely. Mars serves as a real example of this process. Meanwhile, Earth demonstrates how a strong magnetosphere can maintain the conditions necessary for life over billions of years. The comparison also highlights a deeper truth. Planetary habitability depends on more than just distance from the Sun. It also depends on internal heat, core composition, atmosphere dynamics, and the ability to resist the relentless pressure of stellar winds. Mars once had many of these ingredients, but without a lasting magnetic shield, it could not hold on to them. Through the story of these two worlds, we gain perspective on how delicate a planetary environment can be. Earth continues to thrive under the protection of its magnetic field, while Mars reveals what happens when that protection is lost. Together, they show the crucial role of magnetic shields in shaping planetary destiny. When scientists look for signs of life on Mars, they begin with one guiding principle: follow the water. Every place on Earth where liquid water exists, no matter how extreme the environment, life has found a way to survive. Because Mars once held rivers, lakes, and possibly shallow seas, these ancient waterbeds have become the primary targets in the search for past life. One of the most compelling regions is Jezero Crater. Billions of years ago, it was a large lake fed by a winding river that formed a broad delta. Deltas are excellent locations for preserving biological material because sediments settle gently, burying and protecting anything that lived or drifted through the water. Today, the Perseverance rover explores this region, drilling into layered rocks and collecting samples that may hold traces of ancient microbial life. These samples will eventually be returned to Earth for detailed laboratory analysis. Clays found in old lake beds add another layer of promise. On Earth, clays are exceptional at trapping organic molecules, protecting them from destruction. Their presence on Mars indicates that water once remained stable for long periods, long enough for chemical reactions to shape minerals and potentially support early life. Some clays form in mild, neutral water conditions, especially favorable for microbial life. Another important target is the subsurface. Even after the surface became too cold and dry, groundwater may have persisted underground. These hidden aquifers could have maintained temperatures suitable for microbial life long after Mars's surface environment became hostile. Some minerals on the surface, such as certain sulfates and carbonates, form only when groundwater interacts with rock. Their presence hints that deep underground ecosystems may have existed. Scientists also examine ancient shorelines and valley networks carved by flowing water. These features suggest long-lasting rivers, not brief floods. Continuous water flow increases the chances that life could develop, adapt, and leave behind detectable traces. Sediments deposited along these channels may contain chemical signatures, patterns of carbon isotopes, for example, that could reveal biological activity. Modern missions use advanced tools to search for these clues. Rovers carry instruments that can identify organic molecules, measure rock chemistry, and detect minerals formed in water. Orbiters scan the planet using infrared sensors and spectrometers to map hydrated minerals and identify promising landing sites. Each mission builds on the discoveries of previous ones, narrowing down the most likely locations to find preserved evidence of life. While no definitive signs of life have been discovered yet, scientists have identified complex organic molecules in Martian rocks, substances that could form from life or from natural chemistry. Their presence indicates that Mars had the chemical ingredients necessary for life. Combined with evidence of long-standing water, these findings keep the possibility of ancient Martian life open. The search for life on Mars is more than a scientific pursuit. It addresses one of humanity's oldest questions: are we alone? Mars offers a rare opportunity to investigate a world that once had conditions similar to early Earth. If life emerged on both planets independently, it would suggest that life might be common throughout the universe. Ancient waterbeds hold the most promising answers. Beneath layers of sediment and rock, Mars may still carry the faint chemical echoes of organisms that lived billions of years ago. These quiet clues, waiting in the dust, guide every step of our exploration and shape our understanding of what it means for a planet to harbor life. Every major Mars rover mission has followed one guiding strategy: go where the water once was. Ancient lakes, river deltas, and groundwater pathways offer the best chances to understand the planet's past climate and to search for signs of life. Because of this, the history of water on Mars has shaped nearly every decision about where to land, explore, and drill. NASA's Curiosity rover, for example, was sent to Gale Crater because it once held a long-lasting lake. Orbital images revealed a massive central mountain with layered sediments, clear signs that water repeatedly filled and retreated from the basin. These layers act like pages in a history book, each one preserving clues about changing environments. Curiosity's discoveries confirm that Gale once hosted mild, neutral water capable of supporting simple microbial life. Perseverance, the newest rover, landed in Jezero Crater for similar reasons. Jezero contains one of the most well-preserved river deltas on Mars. Deltas form where rivers slow down and deposit fine sediments, materials that can trap organic molecules and fossils. Scientists chose Jezero because it offered the highest chance of preserving evidence of ancient life. Every rock Perseverance collects is selected with this purpose in mind. Other missions followed the same logic. The Opportunity rover explored Meridiani Planum, a region rich in sulfate minerals formed by evaporating water. These minerals act as chemical proof that shallow lakes once covered the plains. The Spirit rover investigated Gusev Crater, where a valley system suggests that water once flowed into the basin. Orbital missions helped narrow down these sites. Spectrometers detected hydrated minerals, radar revealed buried ice, and high-resolution cameras mapped ancient shorelines. Each tool guided scientists toward regions where water shaped the geology. Even today, future landing sites are chosen based on the presence of clay minerals, ancient stream channels, or rocks altered by groundwater. By following the traces of water, rover missions have built a clearer picture of Mars's history. They show where lakes once stood, how rivers carved valleys, and how long water remained stable on the surface. Landing where water once flowed allows each mission to study environments that might have supported life and to collect samples that preserve that precious history. Water has been the compass of Mars exploration. It determines where we land, where we drill, and where we search for clues about a world that was once far more alive with geological activity and flowing surface water than it is today. If humans someday settle on Mars, water will be one of the most important resources shaping where and how they live. Future habitats cannot rely on transporting water from Earth. It is far too heavy, far too expensive, and far too limited. Instead, settlers will need to use the water already present on Mars, hidden in ice, minerals, and the thin atmosphere. Understanding where this water is located and how accessible it is essential for any long-term human presence. The most promising source is subsurface ice. Radar instruments from orbit have revealed large deposits of ice buried just a few centimeters to a few meters below the ground, especially in mid-latitude regions. These hidden glaciers offer a renewable source of water that can be extracted by heating or mechanical drilling. Their shallow depth makes them ideal for future bases, allowing habitats to be placed near stable, accessible ice without requiring deep excavation. Polar regions contain massive quantities of water, but their extreme cold and long, dark winters make them less practical for early settlements. Temperatures can plunge far below levels safe for their infrastructure, and sunlight needed for solar power disappears for months. Still, these icy regions may become valuable for scientific bases or long-term industrial operations once technology advances. Another potential resource lies within hydrated minerals. These rocks contain chemically bound water that can be released by heating them to high temperatures. While this method is energy intensive, it could provide water in areas where ice is scarce or buried too deeply. Regions rich in clays or sulfates might serve as secondary water reserves, supporting agriculture or manufacturing inside sealed habitats. Even the atmosphere holds tiny amounts of water vapor. Though the air is extremely dry, specialized equipment could extract small quantities of moisture from it, similar to atmospheric water generators used on Earth in desert environments. While atmospheric extraction would not provide large volumes of water, it could help recycle or supplement supplies in closed-loop life support systems. Water on Mars would serve many purposes beyond drinking. It can be split into hydrogen and oxygen through electrolysis. Oxygen provides breathable air, while hydrogen can be used as rocket fuel or stored for energy. Water also regulates temperature inside habitats, supports plant growth, and plays a vital role in shielding against radiation when used in walls or tanks surrounding living spaces. For these reasons, landing sites for future human missions will almost certainly be chosen based on water availability. Locations with shallow ice, moderate temperatures, and stable terrain offer the best conditions for sustainable habitats. Scientists are already mapping such regions, identifying places where colonies could thrive with minimal energy expenditure. Mars teaches us that even small amounts of accessible water can determine whether a planet is livable. Its remaining ice and hydrated minerals are silent but essential resources, shaping humanity's future exploration plans. If humans one day establish a long-term presence on the red planet, it will be because they learned how to use the water that Mars still holds beneath its surface and within its rocks. The idea of restoring Mars to a warmer, wetter world has captured human imagination for decades. This concept, known as terraforming, explores whether it might be possible to rebuild an atmosphere thick enough to warm the planet and allow liquid water and perhaps oceans to return. While this vision remains far beyond current technology, studying the possibility gives us insight into how planetary systems work and what would be required to reshape an entire world. To create oceans on Mars again, the first requirement would be heat. Today, Mars is too cold for liquid water to remain stable. Its thin atmosphere cannot trap warmth, causing surface water to freeze or evaporate almost instantly. A thicker atmosphere would be needed to insulate the planet, similar to how Earth's greenhouse gases hold warmth close to the surface. One proposed method involves releasing carbon dioxide from the poles and from minerals in the crust. If enough CO2 entered the atmosphere, it could increase pressure and trap heat. However, measurements from orbiters and landers show that Mars does not have enough accessible CO2 to make a significant difference. Even if all known sources were released, the atmosphere would still be far too thin. Another idea suggests importing gases like hydrogen or methane to warm the planet. These gases are powerful greenhouse agents, and in theory, they could raise temperatures. But transporting them from elsewhere in the solar system would require advanced technology and enormous energy far beyond what humanity can currently achieve. A more natural approach involves tapping into Mars's own water. Subsurface ice could melt if the planet warmed, forming lakes or shallow seas. But this would require long-term atmospheric stability, something Mars has not had for billions of years. Without a magnetic field, the solar wind would continue stripping away gases, making it difficult to maintain a warm, thick atmosphere. Still, small-scale terraforming might be possible within seals' habitats. Future settlers could create localized environments with breathable air, liquid water, and Earth-like temperatures. These enclosed ecosystems would not change the entire planet, but they could support long-term human presence. Terraforming also raises philosophical questions. Should humanity attempt to alter another planet? If ancient life once existed on Mars, or still exists deep underground, changing the environment could erase valuable clues or harm potential ecosystems. Scientists emphasize the importance of understanding Mars fully before making irreversible changes. While true oceans on Mars remain a distant dream, the study of terraforming teaches us about planetary climates, atmospheric loss, and the delicate balance required for habitability. Mars may never return to the blue world it once was, but exploring these ideas helps us appreciate the complexity of reshaping a planet and the responsibility that comes with imagining such a future. Mars is not the only world in our solar system that has lost its water. Several planets and moons show signs of ancient lakes, oceans, or icy surfaces that transformed over time. By comparing Mars to these dry or drying worlds, scientists gain insight into the different pathways a planet can take and why Mars ended up as it is today. Mercury offers the most extreme example. As the closest planet to the Sun, it never had the conditions needed to hold liquid water on its surface. Its weak gravity and lack of atmosphere mean that any water molecules striking Mercury are quickly lost to space. Yet interestingly, radar observations have detected water ice hidden in permanently shadowed craters near the poles. Like Mars, Mercury shows that even a harsh world can hold on to small pockets of water if they are protected from sunlight. Venus tells a different story. Scientists believe Venus may once have had oceans, possibly enough water to cover the surface in a shallow layer. But intense sunlight and a runaway greenhouse effect caused the water to evaporate. Once water vapor reached the upper atmosphere, sunlight broke it apart and hydrogen escaped into space, a process very similar to what happened on Mars, but far more extreme. Today, Venus's dense, hot atmosphere holds almost no water vapor, making it the driest planet in the solar system. The Moon provides another comparison. Like Mars, it has no global magnetic field and a very weak atmosphere. Solar wind particles constantly strip away gases, preventing the formation of stable liquid water. Still, recent missions have discovered ice preserved in shadowed polar craters, showing that water can survive on airless bodies if locked away from heat. Even larger icy moons, such as Europa and Enceladus, tell part of the story. These worlds hold vast oceans beneath their frozen surfaces, kept warm by internal heat rather than sunlight. They show that water can persist in many forms and environments, even when a surface appears cold and dry. Mars, lacking strong internal heating, could not preserve its water in the same way. By comparing Mars with these worlds, scientists see a pattern. Water is common in the solar system, but keeping it liquid on the surface requires a delicate balance of temperature, atmosphere, gravity, and magnetic protection. Mars once had part of this balance, but lost it over time. Venus never regained control of its climate. The Moon and Mercury never had enough atmosphere to begin with. Icy moons kept water hidden below. Mars sits in the middle of these stories, a world that had water, lost it slowly, and preserved only fragments in ice and rock. Studying these dry worlds helps scientists understand not only Mars's past, but also the potential fates of planets around other stars. It reminds us that water is resilient, but surface oceans are fragile, easily erased by heat, cold, or the absence of a planetary shield. Across all of modern astronomy, one principle guides the search for life beyond Earth: follow the water. This idea comes from decades of observations showing that everywhere liquid water exists on Earth, deep underground, inside glaciers, around volcanic vents, or even in extremely salty lakes, life has managed to survive. Because water is such a powerful solvent and a stable medium for chemistry, scientists consider it one of the most reliable indicators of habitability. Mars plays an important role in shaping this principle. Its ancient lakes, river channels, and clay-rich sediments show that water once flowed freely across its surface. Even though Mars is dry today, its geological record preserves billions of years of interactions between water and rock. This history helps astronomers understand how water behaves on other planets and what kinds of environments might support life. Water's importance goes beyond simply being a liquid. It helps regulate temperature, dissolves minerals for chemical reactions, and transports energy within a planetary system. On Earth, these properties allowed early life to emerge in shallow seas and hydrothermal environments. If similar conditions once existed on Mars, they could have supported simple microorganisms, even if only for a brief period. When scientists examine planets beyond the solar system, they search for signs that water might exist there as well. Mars teaches us that planetary change does not happen quickly. The world we see today, a cold, dry planet with a thin atmosphere, was shaped across billions of years by slow processes that, taken individually, seem almost gentle. But over vast stretches of time, these small forces accumulate, transforming an entire planet. One of the first major shifts occurred when Mars began to cool. Because the planet is much smaller than Earth, it lost heat faster. Early in its history, Mars had a warm interior, active volcanoes, and a magnetic field that protected its atmosphere. During this period, rivers flowed, lakes filled, basins, and water interacted with rocks for millions of years. But as the interior cooled, the magnetic field faded. This one change marked the beginning of a long decline. Without magnetic protection, the solar wind began to erode the atmosphere. This was not a sudden, violent event. Instead, it happened atom by atom, slowly thinning the blanket of gas that kept Mars warm. Hydrogen escaped first, then heavier gases. Over hundreds of millions of years, Mars's skies grew thinner, its climate colder, and its water less stable. At the same time, volcanic activity faded. Eruptions on early Mars helped replenish the atmosphere with carbon dioxide and water vapor. When these eruptions stopped, the atmosphere no longer received fresh gases. The decline accelerated. Less air meant lower pressure, and lower pressure made water evaporate or freeze more easily. Dust storms, chemical reactions, and changes in Mars's tilt all contributed to the transformation. Seasonal cycles redistributed frost, ice migrated beneath the surface. Minerals captured water within their structures. Each process made only a small change in the moment, but over geological timescales, they reshaped the entire planet. This slow transformation offers a powerful reminder. Planets evolve at their own pace, and that pace often stretches far beyond the span of human lifetimes. A change that seems insignificant in a year can alter a world over 1,000,000 years. A steady process, repeated billions of times, can erase oceans, carve valleys, and create new climates. By studying Mars's long timeline, scientists can better understand how Earth might change in the distant future. Our planet also experiences shifts in climate, magnetic strength, and internal heat, but over much longer periods than we can easily imagine. Mars helps us see these processes more clearly, like a sped-up example of planetary aging. The story of Mars shows that planets a history written across stone layers, dried riverbeds, and frozen minerals. Understanding these timescales helps scientists recognize that Mars was once very different, and that given enough time, any planet can transform into something new. The story of Mars is more than a distant planetary tale. It is a mirror that reflects possibilities for our own future. Mars once had running rivers, standing lakes, and perhaps an ocean that wrapped across its northern lowlands. Today, it is silent and dry. Its atmosphere is thin, its surface frozen, and its water locked away in ice and minerals. Understanding how Mars changed helps us understand the conditions that keep Earth habitable and how fragile those conditions may be. One of the clearest lessons Mars gives us is the importance of atmospheric protection. Without a strong atmosphere, a planet cannot keep liquid water on its surface. As Mars lost its magnetic field, the solar wind stripped away its air, slowly removing the gases needed to trap heat. This reveals how delicate the balance is between a planet and its star. Even small changes, stretched across millions of years, can erase oceans and transform a climate. Mars also shows how deeply a planet's interior influences its surface environment. As Mars's core cooled, its magnetic field faded. As volcanic activity waned, the atmosphere stopped receiving new gases. On Earth, active geology continuously renews our atmosphere and helps regulate climate. Mars's transformation illustrates what can happen when this internal engine slows down. The disappearance of Martian water also reminds us that habitability is not guaranteed. A planet can shift from life-friendly to harsh and barren through slow, natural processes. This long timeline encourages scientists to pay attention to subtle changes on Earth. Changes in atmospheric composition, magnetic field strength, and climate patterns that could have significant effects far into the future. At the same time, Mars offers hope. Even after billions of years of atmospheric loss, the planet still holds water. Ice remains at the poles and beneath the ground. Minerals preserve bound water that has survived since ancient times. These remnants show that water is resilient, capable of lingering long after surface environments change. For future explorers, this water may become a resource. For scientists, it is a record of a world that once supported conditions not unlike early Earth. Beyond practical concerns, Mars prompts deeper reflection. It asks us to consider how rare or common habitable environments might be in the universe. If Mars once had the ingredients for life but lost them, how many other worlds might follow similar paths? How many could still be habitable today? Mars's story encourages us to look outward, searching for planets that still hold the warmth and water needed for life. In its quiet landscapes, dry riverbeds, layered sediments, frozen basins, Mars shows both the fragility and resilience of planetary environments. It reminds us that worlds change, often slowly but profoundly, and by studying Mars's past, we gain insight into our own planet's future and into the care required to preserve the conditions that make Earth uniquely alive.